Dr. Sylvia Mazzoni began her career in earthquake engineering in the late 1980s as an undergraduate student of the late Professor Nigel Presley. It's a small world, the earthquake engineering profession. When she tested her first reinforced concrete column in the lab. Her PhD studies at UC Berkeley focused on testing of reinforced concrete beam column connections under the supervision of Professors Jack Maley and Steve Mahon. Right after finishing her PhD in 1997, Sylvia joined the OpenSea's development team as the user support manager. In this role, she wrote the OpenSea's manuals, as well as developed the curriculum for the OpenSea's Days workshops. In 2010, she joined Dagenkolb in the New Technologies group, where she developed their probabilistic seismic hazard and ground motion selection capabilities. In 2013, she joined the NGA project and developed the peer NGA ground motion database web portals, NGA West 2, NGA East, NGA Subduction. Many portals I'm sure all of us, or many of us in this room, use regularly. In 2020, she rejoined the OpenSea's leadership team and is also contributing as a developer. In 2020, she started Sylvia's Brainery, a self-funded consulting entity providing access to live and online courses, as well as web applications, and provides consulting to researchers, practitioners in OpenSea's application and development, as well as seismic hazard and ground motions. Sylvia is also now working with the Design Safe applications team to improve and expand the integration of OpenSea's and other applications in the Design Safe cyber infrastructure. I've personally had the pleasure of knowing Sylvia for quite some time now. After one of my earlier interactions with her, I invited her to come and talk about OpenSeas to myself and my colleagues in an attempt to upskill ourselves in OpenSeas. I'm sure she left that initial workshop realising what an uphill battle she had. I noticed that she is extremely passionate and extremely knowledgeable in everything she does, and I know that many of us are going to learn a lot and take away a lot from her talk today. So with that, I will pass it on to Sylvia to talk about the intersection of research, practice, and standards in performance-based earthquake engineering, seismic hazard, ground motions, and numerical simulation.
Good morning, everyone. My name is Sylvia Mazzoni, and I am here to talk about a few different things that I'm interested in. Dion sent me an email a long time ago with a list of topics that I could cover, and each one I'm very passionate about, so I'm going to try to cover all of them. And I think I can, but of course I forgot one of them, so I actually have to append seismic risk to that list as well. I think we can get through it. I'm excited to have a big audience that we can actually explore these different topics and big words that everybody uses so easily, and really try to look behind them and try to have a better understanding. So my goal is to give you a warning. I'm hoping you'll walk out with more questions than when you came in, because I want to expose you to all these different ideas that are always inside a black box, and I want to start looking inside a black box, see what these different topics are. I'm going to show you how they all kind of fit together, so that then when you go home, you can go, oh, wait, what was she talking about? I like to learn a little bit more, and you can go down that rabbit hole that I found myself in every day. So here's the outline of my talk. We're going to talk about, how everything fits into performance-based design, the different realm that I work in research, standard, and practice, and how those work within the 4 different topics of seismic hazard. We talk about seismic risk, ground motions, and I can't leave OpenSeas out, so I have to talk about that as well. This is an interesting gear system, because if you actually try to make it work, I don't think the gears would actually turn. So I thought it was highly metaphorical to use this image. So first we're going to talk about what's on the left-hand side. Everything here is backwards, but that's still the left side, right? We're going to talk about these different planes of the research, the standard, and the practice, because they do work well together. It's actually really important. So many people are only, focused on the research, but the research has to have an objective of informing the practice. And so in research, you do the creative work, quote unquote, where you actually look at the data and you have the time to develop models, improve models, iterate, and really spend a lot of time doing some even creative thinking. But then that gets passed on to the practicing engineers who actually have to solve individual problems. And oftentimes, you can take what comes right out of the research very fresh and apply it to each project in different ways. And that is great, but you have to work within the bounds of standards, the building code. And so that's where the standards in the building code come in, because they need to set up a minimum standard for all practices and almost define a common language, because otherwise, if you have one engineer doing one seismic hazard analysis and compute risk, and then somebody else does it differently, it's really difficult to then resolve and put everything together. So it's really important that these three branches really work well together and communicate. In the US, I'm involved, and I know there's something similar going on in this country right now with the new seismic hazard model. I'm involved with what's going on right now with the building standards. In the US, it's always a continual race. So right now, we're working for the building code that's going to come out in 10 years down the line. And it's a two-phase process, and you'll see that I will address it. First, there's the PUC, which is the Provisions Update Committee, where we do the studies and the, really looking at the problems and untangling and developing proposals that we have to vote on as different committees, but then they get passed on to the ASC 7 committees that they themselves look at these proposals from the PUC and actually then put it into ASC 7, which becomes a standard and law. So it's a long process of looking at the research and the practice, and there's people involved from both fields in developing these standards that are consistent and usable. And oftentimes there's conflict between these three different branches. And so it's important to have an understanding that those three branches are always there in everything that we do in trying to improve the profession. You can't do one without the other. And so now that takes us back to the overall view, and what I like to do is now go through these individual topics of seismic hazard, how that leads to the computation of seismic risk, ground motions for analysis, and then of course the analysis component. So it's a progression of the different aspects of performance-based design. So let's have some fun. I'm going to get technical. We're all engineers or speak the engineering language. So I'm not afraid to put in a few different concepts. And I hope that you can ask me questions at the end and have discussions throughout the conference. So again, my job here is to really shake things up a little bit. That's what I do. I'm a little earthquake. And hopefully that will then lead to more knowledge and more understanding from everybody and everybody asking questions. It's really important. What I find when I work, in some committees of, just practicing engineers is, well, why is this in the building code? Why do we have to do this? And so it's important to get involved with it early on, and so that you can have your voice and be heard, so that you can be part of the decisions that are made and also have a better understanding and appreciation of the decisions that need to be made, because it's really about building consensus. We need to do the best that we can, but I think we need to also build a consensus, which is what the standards are all about. So let's start looking at, let me go back. So to kind of give you an overall view, so we've got the seismic hazard, which is the science, is quantifying what is the seismicity at your site. And I'll talk about the different causes and the different aspects of the seismicity and how we quantify it. Seismic risk almost brings in now performance objectives, where we can talk about, what is the risk of collapse is what we talk about in the US. Here you talk about casualty risk, or fatality risk. It could be financial risk. There's just so many different metrics in risk, and it's very important that we identify which ones we're talking about, especially in the seismic risk world. Ground motions are used to then, you take what comes out of the risk or the uniform hazard spectra, and these ground motions are either used in analysis or even just the spectra are used as your minimum forces or minimum requirements for your building. It was interesting, I was in the middle of one of these meetings, and one engineer, practicing engineer, is like, well, what if we want to do more? Can we please specify in the building code that people can do better than what's in the code? And it's like, but that's the name of of the code is a minimum requirements. So you can always do better, you can always do more, and so we need to set up a language that at least is common for everyone. And then the numerical simulation is, quote unquote, the most important part, is the final product is, and as a structural engineer, that's what I'll work on, that we need to have good models, not just in the hazard and the risk, but also really good structural models. And that's something that we do a lot in the research, and it's really neat to see how that's transitioning also in practice. And that's where I'm gonna end with in this presentation. So, seismic hazard. There's two types of seismic hazard analysis. So it's pretty much, it's a comprehensive estimate and quantification. We're really getting down to numbers of the shaking at your site. It considers all possible events. You're not just, by one fault. Typically, you're surrounded by many faults, especially in New Zealand. And so you can do a deterministic seismic hazard analysis. This is important because I'm going to talk about a deterministic cap that we use in the US. Where in a deterministic seismic hazard analysis, you're doing an envelope of the critical scenarios, or the, what is the latest? The maximum credible scenarios for each fault, and you envelope over all of those to get your design forces or your design spectrum. Sounds pretty easy, but it's actually not trivial, because how do you define what is the critical magnitude for your fault? And what range do you take the mean? Do you take the mean plus 1 standard deviation of your estimated ground motions? And so it's almost something that you can put into the spreadsheet, and so the computational part is easy, but the decision making of knowing what to put into that spreadsheet is really, really important. And so it's no longer trivial, and it can lead to different interpretations. So it sounds easy, but again, it's really all about what you put into your model. And then we go into probabilistic seismic hazard analysis, which has really become the default. And it's a much more comprehensive approach, because you're looking at all possible scenarios, in which each scenario you assign a probability of occurrence. So small earthquakes are more likely to happen than large earthquakes. So sometimes if you're near a small fault, that can actually be controlling your design versus a very large fault that's just a few miles down the road, just because of the frequency of the earthquakes, and also takes into account the contribution of many different faults. If you're in a situation where we have a few different faults that actually increase the probability, they don't affect the probability of happening as much as we're looking at increases the probability of actually exceeding the ground motions. And so you increases the probability of failure in your structure if you don't design it appropriately. And so these are the two types of analyses that you want to learn about. They're really interesting. The math is pretty straightforward on them. But I think it's really important as structural engineers who are using ground motions to have an understanding of where these ground motions actually come from. It's pretty straightforward, and it's actually pretty neat to see behind it. And then, so what I want to do is I want to just kind of dig into that a little bit. And so let's look at what the different characteristics that affect your shaking at your site. So one is the source, the fault type, whether you have crustal or subduction faults, the path, how far you are from the site, what kind of, if in subduction, does it have to cross a volcanic arc or not? That's the easiest one. Your site amplification, if you're on rock versus on soil. And the last part is also your building type. We can talk about the next step would be, your building strength, but on the hazard side, you kind of stop at just what is your fundamental period and damping of a simple single degree of freedom system. So it's just about structural type, not really structural behavior. And so these are the 4 different steps that you go through. New Zealand is a beautiful country. We flew in, my husband and I took advantage of this trip, and we flew into Queenstown a few days ago. I've lost track of time. It's all been T-minus today. And we visited South Island, beautiful mountains, beautiful steep mountains. And of course, those are right along the lines that you see of the faults in these crustal faults right here. Each one of those faults gives us some beautiful scenery, but it also gives us earthquakes. So that's the beauty. If you read the abstract, that has not much to do with the talk, it was just an introduction to show how important and earthquakes really have a beauty to them, as well as just having to deal with the consequences in the built environment. So New Zealand is fascinating because it's a small country, small population, but it's got everything that an earthquake engineer would like to have. You've got these crustal faults across both islands. There's a tiny little corner up on the left-hand side that I haven't quite visited. That seems a little bit quiet there, but I think it looks like it used to be an old volcano anyways. So you've got your crustal faults, and then you've got the two subduction zones. And I'm originally from Italy, and we have a very similar situation. We've got the live volcanoes, and we've got the subduction a little bit down in Sicily, as well as these beautiful crustal faults that cross for us is the Apennine, what you call your Alpine mountains. Those for us are the Apennines, and then our Alpines are the Alps up north, which I think that's a subduction thing. So point is, beautiful countries, New Zealand and Italy and California on the West Coast, we've got everything as well. It just brings in all these different aspects of earthquake engineering that we need to take into account. So crustal events are relatively shallow and more frequent, and they're typically, as you can see in the figure, they're on land, so they may have a bigger impact. And then you've got subduction events, which is when the oceanic crust goes under a continental crust or a tiny little continent here. And so those are deeper, but they can be bigger earthquakes, but typically they're farther away, but then they can come with a tsunami as well. So it's really important to look at these different aspects and the effect of different regions of the country, some the same regions as well, and they all have different behaviors because if you put them together, we look at magnitude and the probability of exceeding a certain magnitude. And so you can see in the graph that we've got the crustal faults that have smaller magnitudes for the same probabilities, and then we've got the two different subduction forces or sources that have a different magnitude probability or magnitude rate relationship. This is really important when you do seismic hazard analysis that you don't take into account when you're doing deterministic analyses. What is the likelihood of this magnitude? And if we take these and we look at the second part, or second and third part of our process of what affects your ground motions, it's your site, is where you at and how far are you from each one of these different sources. So I picked 4 different points on the map. Each one has a different combination, different flavors of the 3 different faults. So it's really important to what types of sources you are and where you are with respect to these different faults. The next aspect is what kind of building you're in as well. So tall structures have a longer period. Let's say they all have the same mass, while short structure have much higher frequency response, and therefore they respond different parts of your ground motions. And so what we do is we look at the response of a single degree of freedom oscillator, and this is going to come in later important with what I'm doing with the open seas on these models being important. And you'll have, it really depends on the type of structure that you have on the different types of soil. And so there's a lot of data that has been collected in the NGA programs and also as well as some other more regional programs where you can develop a relationship between, for your scenario, so you have a given magnitude and given distance, and now you can get the spectral acceleration, which is really your design forces, versus period, which is the characteristic of your structure, for each scenario. And so you look at each one of the different faults that is around you, and I'm sorry that the graph at the bottom is actually from the US because it was a nice figure to have. Different faults are going to have different probabilities for the different magnitudes. So you take the figure on the left and you do some math along with your response spectrum. And so then you develop what's called the hazard curves. For every period, every point on your graph, so you're interested in your one period of your building, and different site class, you develop these hazard curves, which is the probability of exceeding a spectral acceleration. So now we've gone from magnitude to design forces, right? And so that's what you have for each one of your sources, and then you add up all the different faults all together when you're doing probabilistic seismic hazard analysis, and you get the total hazard at your site, okay? And that's the dashed black curve. So now you have a site and a building and the site class, And you can look up these curves, and they're wonderful. They're mapped. There's a great website that comes with the new hazard model for New Zealand, where you look at the probability of exceeding a certain ground motion. Well, this now leads to what's called the uniform hazard spectrum, because now what we want to do is give me for all the periods of your site, or we can do it for the entire country or region, is what is the spectral acceleration that has a certain probability of being exceeded. So in the US, we work in the NZSEE world. So we're looking at the 2% probability of exceedance. It has a return period of about 2475. And so now we're looking at what is the ground motion that is likely to happen, or it has this level of probability. And that's what we designed for when we're doing the uniform hazard spectrum. In New Zealand, and so that previous number, it could be whatever you want. It really depends on what evaluation you're doing. Now, when you now bring in the standards that come in and set up a minimum, in the US, the uniform hazard spectrum is based on the 2% probability in 50 years of being exceeded, and then we take 2/3 of that. And in New Zealand, you're looking at the 10% probability of exceeding a certain ground motion. And so that's what the uniform hazard spectrum is, and that's what all the different maps, and this is what forms the basis of design for your structures. And so that is what, it's a 10 and 50, or sometimes we talk about in return periods, which is 1 over this probability of about 475 years. So a ground motion that is likely to be exceeded in about 500 years itself. Now, if you take that and you can compute this for the entire country, and that's what you have in these different maps that come from the seismic hazard model. So there's a website that I gave. So now if we look at this, what this is telling us is, and this is an interesting issue when you draw maps and you look at the color scale. The color scale is a little bit extreme, but I think it's because that way you have the same color scale for different periods and different site classes, okay? So this figure right here, so this is the map, and this is for a specific type of building, a period of 1.5 seconds. So this is a moderate, it's not a tall building, it's just 1.5 seconds is somewhere right in the middle there. It's a good representative of seismic demands. And as long as you're always looking at the same period when you do the comparison, then you're okay, because it's all relative values. And then the other thing that you look at is the site class, which is a 400 meters per second. So this is a relatively soft soil. And so this map tells us that there's this whole line of, the lighter, the higher your design force is, which means if you're designing based on this 10% probability of exceedance in 50 years, you literally look up in this map and you find out for your period and your site class, you look at what your design forces need to be. And so as you can see along this line, and there's a tiny little circle over here that actually has the highest design forces. So this tells you the regions, and assuming it's the same period or same structure in different parts of the country, for a specific site class. Okay, because if you're in the hills, you have a different site class, and that would be the next step. So this is a good way of looking at the uniform hazard across the entire country. The math behind it is interesting. I think it's really important to be able to break it down and look at what kind of faults will control your design forces in there. So this is what the uniform hazard spectrum is, and that's where I find it interesting, because the first speaker this morning was talking about this, where there's nothing you can do about the wind. And so this is where I kind of draw the line between the science and then the engineering. There's not much that we can do on the hazard, okay? We could choose different hazard levels and things like that, but what you do with those really comes into the engineering. And in the US, we've turned this into looking at actually seismic risk and uniform risk, and we look at a risk of collapse. I know that in this country, you do things on the uniform hazard spectrum, which I think is much easier for us to visualize and understand, because it's forces. It's a little bit easier to calculate and explain, but it's really difficult to compare it to other metrics, right? So if you're designing a building, you're designing not just for earthquake, but you're also designing for wind. And so in the US, we had to bring that up to the level of risk so that you can then kind of speak at least the same language when you're doing design. So risk just adds on an additional integral to the task, and I think it's kind of cool. And so now we're looking at developing uniform risk spectra. And that brings up an interesting topic, which I think is a topic, a quantity that a lot of people kind of take for granted is computing these fragility curves. Everybody in structural analysis is into developing fragility curves. The issue is a lot of times it's just really bad models, and then we take these numbers and move forward. But what's interesting, though, is if they're bad models, then maybe we should just look at something simple and uniform. And that's what the USGS and the US has done, just looking at a very standard fragility curve. And what the fragility curve gives you, again, now every time we're doing from one line to the next. Remember, we were at spectral acceleration and probabilities of spectral acceleration. Well, now we're going to look at what is the probability of being at a certain damage state as given a spectral acceleration. Okay, and so that's what the fragility curve gives you. This is a typical figure from, I think, the Hazes, and I think it gives you a really good image of what risk means quantitatively. If you've got strong shaking, you've got some buildings where you have a low likelihood of having small damage, moderate damage, and high damage. And so you can develop these for different types of structures. Now, you can take this fragility curve and combine it with your hazard curve. That was the last curve that we developed. And so now if we integrate this over all, remember I was telling you, sometimes even the small events have bigger consequences than large events. And that's why the probabilistic realm works, because it takes everything into account with very simple and clean mathematics. And so now we can go to risk of collapse, which is a probability of exceeding a certain performance objective. In the US, we've looked at collapse. Given the hazard curve for your site, as well as the fragility, probability of exceeding a certain performance objective given the spectral acceleration. So the math really works out really nicely. And so that's where the risk integral comes in. This is just a graphic that I want you to look up, and this is some work that was done by Nico Luca, is that in the US, the uniform risk spectrum is you're selecting the ground motions. We still have to go back to our spectral accelerations that give you not the same probability of exceedance, but they give you the same probability of exceeding a performance objective. In the US is collapse. How you define collapse is a whole other story as well, okay? But that goes with the fragility curves. So it's pretty straightforward it's just an iterative process, and we're still looking at spectral accelerations, but the ones that give you the uniform likelihood of exceeding a certain measure. And so if we map this, and I've only done this for US because I can't quite do this for New Zealand, you get something like this, okay? So this is a uniform risk spectrum. Right now, in the PUC and ASC 7 committees, because they're kind of going in tandem, we're looking at what are we doing with the deterministic capping, which is the next step that's going to come in here. And so I had to develop a whole lot of maps to kind of quantify what are the different alternatives. So this is the first step. This is, if we do that uniform risk calculation and we get all the spectral accelerations that give us a 1% probability of collapse across the entire nation, you have a map like this. And I live down in LA now, so we're pretty safe. We're only in the dark green, so we don't have to design for super large forces, okay? So if you look at this map, and you'll see that right along the San Andreas Fault and this is for a certain spectral acceleration for a certain period, so this period of 2 seconds, and a site class BC. This is the accelerations that you would have to design for if we used a uniform risk spectrum, okay? I showed you the uniform hazard spectrum for New Zealand. This is the uniform risk spectrum for the US. Well, it's beautiful, but there are some red spots that go all the way to 5 Gs, okay, even in that. But this is a stiff soil in this short period, so you'd expect relatively high values. For some reason, people want windows and doors in their buildings, okay? If you don't need windows and doors and you're building a nuclear reactor, go ahead and work with the uniform risk spectrum. If you want windows, it's gonna be really expensive to design for such large forces and being able to put the details and the strength into your structure to have enough strength and ductility at such large levels. And so then this leaves us with kind of a difficult situation because it's just not impractical. And so Nico Luco at the USGS has done a cost-benefit analysis, and these design forces are just too high to really want to have people build in places like LA and San Francisco. Actually, San Jose and El Centro are really the highest accelerations because they've got two faults that are really close to each other and things get interesting there. And so then this is when we go from engineering to the standards. We've got to come up with something that works and that works for everybody and that everybody's happy and it provides safety to the public. So that if somebody goes in and designs a building, whether it's a small structure or whether it's an expensive structure, everybody has a certain level of safety in the buildings, and we can have cities function. Because if you have a lot of damage even to the small structures, you lose your population and there goes your resiliency and all those metrics associated with it. So we've got to switch over to something that's called risk targeted. So it's not uniform risk, it's risk targeted, which kind of gets a little bit messy, okay? So what we've had to do, what's been done in the past, is to bring in this deterministic capping. And I wanted to show you here that deterministic capping gets complicated. Remember I told you that at the beginning. How do we define it? And so what we do is we do a deterministic spectrum, which is, as I told you before, the envelope of all these critical cases. And it's really hard to define these cases, especially with the new hazard models where many faults trigger each other and there's different combinations. So it's really difficult to come up with that magnitude at a certain distance. And that's why then there's something called the deterministic lower limit, which is really what triggered all these changes that we're trying to do now in the building code, because the deterministic lower limit that just came into the picture is a little bit, people are not happy with it. Geotechs are not happy with it because it's not really representative of the seismicity of your site. And the purpose of the lower limit is like, okay, you can do a deterministic analysis, but again, you can't just, oh, I forgot that fault. And so the deterministic lower limit gives you at least a lower bound to your deterministic analysis. Then we bring in the uniform hazard spectrum and the uniform risk spectrum that I've already introduced, and you put these, and I'll show you the steps that you do through this, to get this risk-targeted MCE sub R spectrum, which is what we are using right now in the US, and this is what we're trying to redefine and reevaluate with this deterministic capping and make it more probabilistic based in the US. And so it's a neat process. The process is complex but not complicated. Is you compute your 84th percentile for your scenario. First, you got to figure out what your magnitude and distance scenario is for your site. You look at the deterministic lower limit. You take the envelope of those. So this is something you just put into a spreadsheet. But I wanted to kind of give you a visual of this process and how every little thing can actually affect your design spectrum. Then you do your probabilistic analysis. And you take the lower of the two. So first we took the higher, now we took the lower of the two. That's why the deterministic spectrum is really important, because if it's too low, it brings your design forces way low, which could be a great thing, but that actually means that your risk goes up. Then if you're doing a site-specific analysis, so that would stop. The USGS and the map values would stop at that MCE sub S sub S. Site-specific. If you're doing a site-specific analysis yourself, you cannot be below 80% of the mapped values. And so your result design spectrum looks like this. What's really cool in the US right now, we've switched over to the multi-period design map spectra, which means that you've got, the USGS has spectra at 22 periods and more site classes. And so you step back, you go to your MCE, now you're comparing it to a curved, a multi-period spectrum, and the shape is a lot better than when you have a 2-period spectrum, especially with the changes from a site, having to go from the reference site to your site class with your F sub V factors, which really brings up what I think is the best thing about the multi-period spectrum is that they've also increased the number of site classes. And so now there's a little bit better discretization of your site classes. So if you're on the border between a site class C and D, now there's actually, its own category. And so to me, this is the biggest improvement in the map values that you have from the USGS is the multi-period spectrum at different site classes, and the values are computed directly at these site classes. You no longer have to apply the F sub A and F sub P factors of the 2-period spectrum. I'm not sure how that's done here, but I found this to be a much more objective way of getting a design spectrum. And so now that leads us into that little curve that we showed now gives you a mapped MCB sub R. So this is what's in the USGS. This is the minimum. This is what, if you're doing a site-specific, you have to be above 80% of this. So you always are going to go back to the map values. And now you can see the values have gone down, but that was actually a different period, okay? But the values have gone down, but not significantly, which is a good thing maybe, but we're going from a maximum of 5G in this case, because this is site class BC, to a maximum of 4.4. And this is really only in certain regions where the deterministic cap applies. So if we turn this over, right? So these are the design forces. So now let's go back and calculate the effects of doing our deterministic capping, which is why for me it's a little bit disconcerting because the two things are not quite related and consistent with each other. This gives you the risk of collapse across the map of the US. Now, as you can see here, almost everything is green, which is the goal, which is the probabilistic, which is a 1% probability of collapse in 50 years. But along the San Andreas Fault, for this period, you see that there are regions in the San Andreas Fault and the New Madrid where we're actually designing for higher risk. In this case, all the way to 9%. For a different site class D, we're actually designing for 13% probability of exceedance. So it's interesting because we're designing for, if you live along the San Andreas Fault, you have a higher risk. You would think we would design better, but we could only design so much that you actually have a relatively high risk of collapse. Now, if we zoom in, and this is when it's become a big battle, and we have meetings, and everybody has different opinions, but if we really zoom in into these cases, and we look at the maximum values for, this is a site class BC for the same period, and that's a site class D for the same period. Everything is period dependent and site class dependent. So we've got maxima of 9% and 13%. But if we zoom in real tight, and I did these maps, these are really cool. They're interactive. You can click on where you are and search where you are. You see that the highest risk values are actually along these. If anybody's ever driven from San Francisco to LA, which I highly recommend, there's this beautiful hills along the San Andreas Fault, which is exactly where these red spots are. So I've plotted population, and there isn't really that much population in those regions of, the 13%. But we're really looking in San Jose, for example, at, I think 5 to 8% probability of exceedance. So those are like the more realistic numbers. And so we're not really changing, the very small changes in our deterministic spectrum are really shooting up our probability of collapse in a relatively inconsistent manner. And that's really the issue that we're having as doing the computations for design and trying to come up with something that's a little bit better in communicating risk. And so these are, the case in this very specific case for this period. If we kind of look overall at what this effect of using this deterministic cap in the US right now on the MCE sub R, remember, capping the ground motions means that we're increasing risk. But the main issue with it is that it's not consistent how we're increasing risk. The deterministic lower limit has its issues. The computing the deterministic scenario takes actually a lot of work because it's based on the deaggregation of your probabilistic scenarios. And so it's actually a lot more computationally expensive to do these deterministic cap calculations. And it's site dependent, period dependent, and site class. So it's really difficult to communicate, to quantify, but the biggest problem is most people don't even know that we're doing this. Because it's really when somebody asks you, well, what are we designing? What is our risk? The answer is always, it depends. It depends on your period, it depends on this. And so it's really difficult to communicate what is the actual risk at your site. And because we're always talking about risk targeted, and people talk about the uniform risk spectrum, most people think that we're looking at 1% probability of collapse across the US, and that's not what we're doing right now. Interestingly, as we're doing through this process, I get the two questions, there's the ones that work in the West Coast is like, wait, why do we have to have higher risk, right? And then the people who are designing in the East Coast is like, why does California get to have a higher risk? So they're really, and that's what I'm talking about consensus. It's no longer just about what is the right number or what is the right answer, is really what is the number that we are most comfortable with and that we can vote on to improve. And so my take on that is we're kind of missing the risk target there because we're missing the target in not being able to quantify and communicate what the actual risk is. So we're looking at some alternatives right now to take care of this. And I know that there's talks in New Zealand about what to do with these really new high design forces. And my take is, and I'm only going to introduce it here, is maybe you can skip that first trial that we did in the US and maybe come up with something that's a little bit more consistent than the hard wiring that we did with the deterministic capping. So the alternatives we looked at is keep the status quo. This is the only way that we can get people to actually stand up and speak up, because if we cannot come to an agreement on something, we're stuck with what we have right now. And most of us, there's a couple of individuals that kind of like the status quo. Most of us know that we need to do better than what is there. We need to have something that's a little bit more consistent. The problem is there's many different ways of looking at this. Somebody's suggesting even reducing, getting rid of the deterministic lower limit. Some people are talking about keeping the uniform risk across the US, and this would only affect the forces along the San Andreas Fault. We're looking at maybe increasing it to 2% across the US, but then that opens up a whole Pandora's box, because this is not really, it's solving one problem and maybe opening up another one. But this is definitely something that should be looked at later on in time. And so what we're doing right now is what we're proposing is to replace the deterministic capping with capping on the risk, only at the higher hazard locations. And so the way we're doing it is what's on the left-hand side is the current risk. These are just 1 million different sites across the US, is we want to do it if you exceed a certain seismicity level to actually increase the risk target from 1% to 2% gradually, depending on your seismicity, and then capping the risk at 2%, 1.5%. Different values, we're still trying to iterate on what these values are. We have brought up the question of maybe making it period dependent, so that we wouldn't make as many changes to the current forces, but we actually got pushback. It's like, wait, you're trying to make it simple, but now you're making it complicated again. And if you're gonna make a change, do it right away. Don't do these gradual changes. So it's been a really interesting process that we're going through. And so this is an example what a map would look like on, in setting up a risk target. And so now we no longer have this multicolors, we actually go from green at 1% to 2%. And it's very easy to compute and define. And so right now we're fine-tuning on what these different points are. If we turn that around, we look at how much this is going to change our design accelerations, and we are looking at 40, 50% increase in places like San Jose and El Centro. And so that's really what this is all about, is not just about trying to do the right thing, but what is something that can give consensus to the researchers, the practicing engineers, and all the stakeholders involved in building this code. Which then brings me to my other battle, which is on ground motions for analysis. The existing building code, ASCE 716 and 22, has different criteria on taking those design spectra and converting them and developing a suite of ground motions to do your analysis if you're doing nonlinear time history analysis. The current code only has two methods for ground motion modification. You have amplitude scaling, which you just apply a scale factor to the entire spectrum, or you've got this tight spectral matching, which is you modify your records so that your spectrum for each record, each component matches your design spectrum. This really comes up with the issue of variability. The problem is, I caused the problem when it was actually Mark Sinclair is the one that came up with the idea, and he's a fellow New Zealander who's done the work on, we developed a mean spectral matching, which is, and I'm going to have to fly through because I'm getting some little flags down here. It says here I have 8 minutes, and you're giving me 2 minutes, but I know that I need to leave room for questions. So I recommend looking at these different methods because in amplitude scaling, we're just scaling things up. In the mean spectrum modification method, you're actually modifying your ground motions a little bit so that you meet your criteria. And as you can see, your target spectrum is met right on by the average of your suite. Then Norm Aberson is talking about, oh, but you have variability in the hazard already. You shouldn't have it in your resultant, which I kind of disagree on some levels on that. And so he's looking at, you do tight spectral matching just on the resultant. And then there's the component spectral matching. And so what we're trying to figure out is, these are different methods that all try to achieve the same goal. The details are very different between them. And so right now, the ASCE 7 has a 90% discount. You can't fall below 90% of your design spectrum when you do amplitude scaling, and you can't fall below 110% of your design spectrum when you're doing the spectral matching. And so we're trying to figure out what is the right level of factor maybe that you need to put in. So for example, for the mean spectral modification method, most people use a 1.0, but it's not in the standard, and so they have to go to processes to get that approved. And so that's what we're working with in the ASCE 7 and PUC committees, is what is the right level of variability that we need in our ground motions, because that's really the main difference between them, and is this variability a good proxy for variability in the building? So we've got a questionnaire. We're working through this we have the methods, we have the science. How do we now put them into legislature? And so that brings us back to having to reach a consensus. We know the math is there and it's straightforward, but how do we make it actually into something that is legislatable? And there's people that come to me, oh, I know you like this. And as a woman, I get that a lot, is, oh, because you don't like this or you don't like that, versus, oh, I don't think it's technically sound. And so this is what the process of dealing also with educating people and trying to figure out the best solution. Which leads me to something really interesting. Now that we're done with the ground motions is on the modeling. Give me 5 more minutes. I know I'm breaking into your tea time. This is the kind of simulations that we're doing these days with OpenSeas. You can really do some really good vulnerability analyses and really being able to assess the risk for your specific building in evaluation or design. I've done 2 things since I started working with the Holmes folks on, they've hired me to do some ASCE 41 compliant type of elements in OpenSeas. It really turned on the wheel again on how do we deal with legislature, with what is in ASCE 7 and ASCE 41. So I developed a new material as well as a new beam integration to make the practicing engineer's life easier and better and faster, which therefore reduces chances of error and improve the models, because remember I told you the big problem is these structural models. And so I took the hysteretic material, I kept asking people to make it better for me, and then somebody said, well, just do it yourself. So I went in and I modified it, and I've put in, it's got more points. You can do actually an ASC 41 curve. Also, a lot of people, if you're an OpenSea's user, in these simplified models, people like to use the IMK materials. But those were developed at Stanford, and I'm a Berkeley grad. So I had to do better than that. But what I like about those materials, a lot of people use them because they have the envelope degradation. So I put that into this material as well. So it's called hysteretic SM because it's for super material, and I'm sticking to that name, right? Everybody's putting their name on it, but it doesn't describe what it does. At least this one describes what it does. It's a really cool material that's already in OpenSeas, and you can use it for these single degree of freedom analyses that get more interesting when you actually have damage and nonlinearity in your response. Or you can put it into your hinges for your phenomenological hinges when you're doing your concentrated plasticity model, which then brings me to my other contribution, which I think is cool. Oh, and these are the different curves and really cool behavior, just lots of colors and what you could do. Brings me to what I've done with the beam column element modeling. I'm going to skip through this. You can do these distributed plasticity, which means you can distribute the nonlinear response anywhere along your element. Or you can do these distributed hinge. It's called the beam with hinges, where you localize the plasticity or inelastic response only over a finite length. Or what people really like to use, because it's simple and it's in the code, these concentrated plasticity models. In OpenSeas, there's two types of distributed plasticity type of models. You could do the traditional displacement-based element, which you just use a lot of them, okay? It's really nice if you really want to capture the growth of plasticity in your one column test. That's worth doing, but then it becomes really expensive when you're doing a structure. And so in the force beam column element, it's a lot nicer and easier, and you're adding up flexibilities. You run out of cards, Dion. And so people like to use this type of formulation, which is a spring, a zero-length element, then you've got another element to do the rigid offsets, and then you've got your elastic element in the middle. And I get way too many questions on that, and people orienting things in the wrong way, missing a node. How do I deal with this? How do I deal with that? And so I developed a new beam integration that is all that concentrated plasticity is done in one element, and it makes it look like what's on the left versus what's on the right. And that brings me to the last part of this, which is really brings everything together, and I think it's really cool, is the work that we're doing with the Holmes engineers, a New Zealand company, of how can we make OpenSea's modeling ASC 41 compliant? So we've implemented an additional component to OpenSea's where it can actually impose these deformation capacities on a fiber section. So it's an additional step that can introduce the strength degradation. And to me, this project itself leads to a better code compliant model, which is really the goal that we're doing in everything we're doing. And so that takes me to the very last slide of thank you, and happy to answer questions here and there and everywhere in between.